This is the brief on rigid body dynamics and tensor relations. So let's jump right in. We're going to quickly unpack two core pillars of rotation. The complex math that defines an object's inertia, and the critical physical principle that dictates whether a spin is stable or just turns into a total wobble. First, the mathematical side of things. It really gets complex when you have to prove the relation for the time derivative of the moment of inertia tensor. To show it's true, you've got to start with the tensor's basic definition. But here's the crucial link that makes the whole thing work. You use the fact that linear velocity is just the angular velocity crossed with the position vector. It's this relationship that fundamentally connects an object's motion to its inertia. Second, let's talk about the physical stability of that rotation. It really just hinges entirely on alignment. The core idea here is that simple, stable motion only happens when the angular velocity is perfectly aligned with one of the body's principal axes of inertia. When it is, the angular momentum and the angular velocity are parallel, and you get a pure, clean rotation. But, in sharp contrast, if you try to rotate it around some other random axis, well, then the angular momentum and angular velocity are not parallel, and that's when you get that complex, wobbly motion that's inherently unstable. Ultimately, a rotating body's stability is determined by whether its angular momentum and angular velocity are parallel, a condition that rests on the body's fundamental tensor definition.